Okay. This would just turn off the projector.
Oh.
You don't want that.
Okay. So yeah, I would like to start thanking the organizer for invitation. So outline of my talk. So I will talk about to share with you some measurements, including some latest measurements from class 12, in fact. Discuss some problems that we have, like what kind of theory support we need. It may look like provoking you, but it will be in fact asking for theory support for certain things. Some of them, like we'll focus a little bit more on the nuclear part, are motivated mainly coming from the fixed target experiments, but hopefully people will find that useful for EIC as well. So the discussion of the systematics and measurements extraction we'll have later on in the discussion session. I will just show something and then we'll have the discussion about the Monte Carlos. So this is our SIDIS bigger picture with everything involved or almost everything. So we have the proton, we have the current fragmentation that we are most focused on so far. We have target fragmentation, and this was already discussed for a while. We were looking for support in theory supporting understanding of different pieces involved, and you can see from Ted's talk, so some thinking went already there. So we had this exclusive side of the story with the GPDs, as you saw from Andreas' presentation. So life is more complicated, so it's not that we measure one thing, but we may have contributions from exclusive side. So we better understand what is going on there and have some self-consistent theory for description. Then we have our semi-inclusive with the TMDs, and on the other side we have target fragmentation that was already discussed in the TMD week. I'll show some more things. These are I'm trying to beat here, Andreas, with the number of what LK will call 500 TMDs, and in fact they are 1,000 because all these functions are also modified in the meeting. So you have. Okay, so these all these functions, they are appearing as Andreas was explaining. So you have
sounds better now.
So as you can imagine, so they are all coming with a difference in orbit correlations. So depending on the correlation of the longitudinal, transverse, and so on, with the momentum, with the proton spin, with the quark spin. So you are getting a bunch of distributions that are all, in principle, now are kind of systematized. The last one to appear were the fracture functions, which will be relevant for understanding of the target fragmentation. So different functions appear as in the focus at different periods. This was also discussed by Andreas about the orbital angular momentum. So these functions that I highlighted, I will talk a little bit about later on. So going to the current fragmentation, so that I'll also discuss how all these things are interplayed to some extent. Because when experiment measures, it measures everything, basically, especially if you have full acceptance detectors, EIC including. So these you have seen a bunch of azimuthal moments and structure functions that are coming with this modulations azimuthal. The detection of the main particles, which is an electron, a lepton, of course, and then we have to detect some 1 hadron, 2 hadron, and so on. Main SIDIS experiments in the game, the compass, which still has very important measurements and messages to bring. JLEIC will be measuring for next 10 years. Electron-ion collider. So right now we are focused more on the electron-ion collider, but we have to remember that for 10 years we will be getting data from JLab, which we still have to understand. And to some extent, what will be the conclusion will also kind of change the electron ion collider program. So these are JLab detectors that are involved in the TMD studies. So Rolf had in his talk some discussions of the observables. So these high precision spectrometers typically measure with a very high precision some specific kinematics, or things like the ratio of sigma L, sigma T that Rolf pointed out, which requires very good precision for measurements, high statistical measurements from hole A, large acceptance measurements that I'll discuss in more details from glass and hopefully in future from solid. Yeah, I see now this was discussed by Rick, like how everybody tries to cover as much as possible, go as far as possible in the center of mass. But what we will see, so depending on the focus, this or that energy will be more or less relevant. So like coming biased obviously from with the JLab program, so I'll be more focused on the proton understanding of the proton. So what is that understanding of the proton? So what is here? So it's like kind of our cartoon for proton, simplified version with some QQ bars rotating, which then we'll call time tornado. And here is the picture that you have seen for many years. And I think more I look at this plot of P bar over U bar from Trillian, more kind of messages are emerging from here. So what this plot in principle shows is that the non-perturbative region, and here this obviously this ratio above 1 is dictated by the non-perturbative effects. These are the effects that are linked to orbital motion and spin correlations, also the same source. So basically these QQ bars. So these effects are relevant around 0.15. So why I was pointing out about whether we should see something happening around 0.15. And you can see in many different plots here and there that like not to say that all our single spin asymmetries are significant in this region, but also some other cases you can notice this region popping out from mainstream, including these differences in analysis of C.
That you say it's a D-bar over D-bar ratio, so it's some balance, is a consequence of orbital momentum.
Yeah. It is consequence of non-perturbative interactions, which are, I mean, at least in some model, they were traced to these fluctuations coming from the valence quarks. So these are QQ bars.
The same model could, because we have measured certain W production, which is very high useful. They would reproduce this?
Oh, you can check with these models. They probably can reproduce something. This is a.
Okay, I'm just asking.
I don't know about your W production. You can check with them. But this, I mean, we don't have that many measures of where non-perturbative effects are relevant. This is obviously non-perturbative
yes,
effect.
I agree.
You agree with that? So, and you agree that there's not much of the stuff that you can expect at small x. I know theory is normally focused on very large x or very small x, where you can use a perturbative approach, and it was certainly very useful because you can come up with some kind of trends that you can use in parametrizations and so on. But the really big effects that you can measure, and those are the ones that are basically responsible for non-perturbative structure, those are they are big here in this region. So this picture is very relevant.
So the blue curve is?
Look, I mean, there were a bunch of curves from different PDFs. I think this probably is some kind of Huh?
Sigma, okay, see.
Okay, yeah. There are others, and now they are not even going below. So they are kind of the new data seems to be keeping this thinking positive. But what all they agree on is that this goes to zero very fast at small x. Now the same, basically the same structure. We were attributing it to valence region. But in the valence region is where we have this non-perturbative C. So this is something that no extraction procedure ever accounted. In a sense that, I mean, you have C here also, and you have C here, and the C is just one C that you have in all kinds of parameterization. So no one is really separating what is called non-perturbative from perturbative C, while the predictions for the transfer structure of these two different Cs are completely different. This crazy whatever tornado is it was predicted to give you significantly wider transverse momentum distributions for this C, and which means that if you go to very small x, you will have completely different distributions than when you have dominance of this, and probably you can use this plot to quantify the fraction of the non-perturbative C, which should be treated in a different way in the three-dimensional extractions. Unfortunately, these Drellian people were very persistent. They stay one-dimensional, and then it will be very helpful to have PT dependence. So if the whole thing is true, so going to higher QT, you will get even bigger and bigger ratios for this kind of for G bar or U bar. So one of the things will be obviously to study KT dependencies of this C, and also polarize C, by the way, from your W's. Okay, so this the same.
Sorry to interrupt you, but when going to higher QTs, one should get like larger asymmetries.
Okay, so based on this approach, let's say this C, this non-perturbative C, let's call it. It has much wider KT distributions. So like factor of 3. So non-perturbative C, or because of this crazy orbiting or whatever it is, but in the models, it has much wider transverse momentum distribution. So these quarks are much higher KT, factor of 3. And obviously, if you go to, since there is a correlation between KT and PT, so when you go to higher transverse momentum, you pick up more of those in the overall fraction. So that should be, I mean, it should be easy to quantify.
That's too naive.
It is too naive, but if you take this thing as a measure for, let's say, a non-perturbative C, if you take this prediction for the different KT dependence of non-perturbative C, then in the models, at least you can get. If you can do it in a more scientific way, it certainly will be a lot more useful. So for now, what we can see from here, so the simple naive, let's call it conclusion, is that the big effects will be expected here, and those effects are this QQ bars. They in fact in different models they were explaining lambda asymmetries, these huge lambda asymmetries, because of correlations of the orbital momentum of these quarks with the spins, with the U quark spin, and so on. So this object is correlated with the transverse momentum, with the spin of the quarks, with the spin of the proton, and so on. So basically generates a lot of orbital effects that, yes.
I think there are already data which can kind of challenge
if there is a data, it will be very nice too.
No, because there is the width of the PT distribution of the C, of the LHC, and then you can get that from BIC, which probes very different X regions, and if that is all true, then actually you should see a different width of this
PT
so distribution.
You know the region, pick this region, take the other region and compare.
We have shown this data already.
So did you compare them?
I have not looked to the C.
Then look at this and see whether you can see something.
So the point is Drellian is probe the C quark distribution.
What?
Drellian Neptune pair production from fixed target to to collider, the probability of transfer of the momentum.
Yeah, it should be. But where have you seen the really? I mean, I was asking these Israeli people for already several years to see how this picture depends on the transverse moment.
They have differential cross section.
They point me to that where you can actually see that. They
what do you mean? So I will choose tomorrow.
Okay, then we can see that. How it looks.
You cannot really see that because everything is now is consistent with the same.
If you integrate, how differential is that? That's the point. If you integrate over X, you will not see anything, obviously, in PT. Anyway, so we can look at your plots. So this different kind of, I mean, there are some indications, but the main things are also from lattice. We have that all these spin orbit effects, they are obviously large at large X. But one thing was here that it may not be just the valence quark, but it will be the non-perturbative C that is generated by the valence quarks that is responsible for that. Okay, so this perturbative versus non-perturbative thing started long ago. As you know, the EMC were measuring these cosines, and the first time this perturbative versus non-perturbative were confronted in these very beautiful perturbative predictions from Georgi and Politzer. I actually proposed as a test for the QCD, which was very nice with the non-Bremsstrahlung, but appeared to be really marginal effect, even at high PTs of Zeus and Hera, not to say about everything else, and Compass, Hermes, and JLEIC, and everywhere. So all these cosines were totally dominated by non-perturbative Kaon type of contribution. So you can produce all these asymmetries in the perturbative limit, but when you go to real life, then they typically come out pretty small compared to non-perturbative part. To make the so to extend this, if you look at our EIC, so if we want to understand non-perturbative effects and see in particular, we have to be very careful in going to very high energies. These are the projections for the Sivers asymmetry measurements from our white paper, where we have different S going from 15 to 100. And you see that this range above 10-2, where the non-perturbative effects are significant, this range basically is missing, at least for this 10. For these statistics, but even if you increase it 10 times, it still will be very challenging to measure something in the X above 10-2. Now, another thing that you can see from here is that normally what we consider all the Sivers and TMD business exciting are things called evolution. And so you don't see much of a Q-square dependence you can get out of here. And since if we really want to study evolution, then we should have projections for evolution of as a function of Q-square, then understand whether this statistics is good enough or it is not good enough. So some input should go there to indicate that something except X dependencies are also relevant. And I think also PT dependencies will be relevant. Those are the things that really describe the Sivers function. So conclusion here is that if we go to lower energies, let's say for T5 for compromise, that will be the optimal for studies of this kind of observables, and it will be important also to overlap with JLab. Where we will be studying this kind of effects for next 10 years. So it will be critical. So as you see from different analyses presented here, things are pretty complicated. Already now, without even starting the measurements, we can see that will be a challenging measurement and will require a lot of theory input. These are the projections that we had for some PT dependencies and Q-square dependencies, which normally are not the main focus of our plots that are mainly showing X dependence. So this plot of the double spin asymmetry as a function of PT is supposed to remind us that the G1 is also TMD. So, and it is important to understand the KT structure of the helicity distributions, which are kind of in the shadow, because people are also so much focused on the Sivers TMD and F1 that the helicity KT dependence, which can be very different. And there are measurements of X dependencies of all kind of polarized PDFs, but not much about the KT dependence. And KT dependence will depend on the polarization. And since the quarks are typically polarized, they are always polarized. So F1 will be the sum of these two distributions, and the G1 will be the difference. So both are relevant if we want really to understand the orbital structure of the PDFs. Okay, so as you see, so in this range, so with a relatively moderate, let's say, energy for the EIC, we can have a really coverage in this 0.1, 0.2 region up to a very high Q-square, which will be important. So it's clear that you go to higher Q-square, you get much cleaner physics. But on the other hand, you also get much smaller effects that typically, and that there should be some compromise in trying to measure all these observables. The way normally we were proceeding is that so we produce some kind of observable. So we measure certain quantities. Typically, those are multiplicities or asymmetries, hopefully cross sections in the future. So make some kind of tables. So far, haven't done much of event level analysis. Then this input is going. Theory is coming up with some kind of description of the structure functions, and then trying to extract parameters. So the way we store the data is still we are still optimizing that, and I think there's still more work to do to understand what is the best way to communicate with theory from what kind of observables, which binning, for example, the EIC projections I was showing, there were, let me go back to that. So you have here, for example, PT bins in 0.2. Is that enough to get some information about KT dependence of Sivers, or it is not? So what will be the binning to study KT dependence? What will be the binning to study Q-square dependence? So for that, first we have to, it will be important to optimize all that kind of data presentation to understand there should be some collaborative work with the theorists, so it will go back and forth until the best way of the analysis will be set up. Right now, the way we have, of course, is good for handling like small statistics, but once we go to precision measurements, it will definitely not be enough. This is the simple example how the analysis was done typically, for example, or you take a very simple structure function like people were doing before, or you take a more sophisticated structure function, plugging into your analysis, and those were also presented and discussed. I have the message from Andrea, who is collaborating with us on this, understanding how the extraction works, what kind of systematics you encounter. And so as a conclusion he had, this is part from his talk, I just copied, that so far people didn't pay enough attention to fragmentation part in analyzing SIDIS, and what is also very important is the faithful Monte Carlo implementation of TMDs, basically. So those are critical things to pay more attention. So this is also a table from his presentation. So we have with these different structure functions, including different data sets. Someone includes, someone is not including. One thing that is missing in all basically extractions are some processes, some contributions that I would like to discuss. So some kind of systematics that will be related to physics that we don't understand very well. So here is the picture from their extraction. So when you add the Drelian, you have kind of different. This is hadronization KT versus intrinsic momentum KT. So you can get different distributions, adding the data, and there are obvious correlations. And so for these 4 points, I just put what kind of PT distributions you will expect if you have their particular model. And so you see that you definitely need a relatively large transverse momentum to be more sensitive to this kind of extractions. So there's a extraction of the transverse momentum dependence of all observables is critical. This is from Ted Rogers' presentation. So for a while, theory was ignoring our kind of complaints about missing pieces of physics that we may have problems with, but should be accounted. So this was already discussed in details. So I think it's a very important work that people are doing. Maybe it's scaring some experimentalists, but it is important to know all your problems if you want to go ahead with the analysis. So you see there's a target fragmentation region now officially present in things that we have to understand. Mass effects that were also relevant in the analysis, and systematic diagnostic tools that will be part of discussion for the Monte Carlo that we want to have. So steps for extractions were like what is that faithful Monte Carlo and diagnostic tools. So we should have obviously, as you saw, a bunch of things contributing, exclusive processes contributing, and so on. So we should be able to have generators that are realistic, should be able to put all these generated events into detector, reconstruct them, add all kind of effects that are contributing to experiments, things like radiative corrections and so on, and be able to quantify the systematics from the different kind of contributions that are or not included. Now, one of the things that will be something that Monte Carlo will be definitely needed are the effects that are not really accounted in the theory. Those are phase space effects. So here are some comparisons of different Compass, Hermes, and then with the JLab, different PT distributions with the different slopes, which to some extent are related to phase space limitations. From when you go to lower energy experiments, they are not just able to generate. There is no physical energy to produce higher PTs for certain in certain kinematical conditions. So the questions that where all these PTs are coming, some people still continue using the Gausses and so on. So these all are the effects that are now people are trying to understand where the PT is coming, and these big differences in the cross sections to some extent are coming from theory trying to bring perturbative description up to very low PTs where it is most likely not applicable. So far, we never converged on the story. So all these PTs around 1 or 2 GeV, where they are actually coming. They are non-perturbative, perturbative. What is the mechanism, and so on. So this is the comparison, like we were just talking about cross sections of JLEIC. And here is one of the first results that we have from class 12, the preliminary presented in DMP. And this is a pi0 multiplicity. So to contribute in that, one of the main things I wanted to point out is that we actually have to extract our own fragmentation functions to understand the systematics from there. And here is the place where you can extract the fragmentation functions. Pi0 is a little bit better than pi plus and pi minus in the sense that here what you can see basically you detect your electron, you detect 2 photons. If you understand your 2 photons, and here you can see the invariant mass of 2 photons compared to Monte Carlo, which is in a very good agreement. So you can describe your efficiencies, and then this basically comes online. This kind of measurement, it will obviously require some more systematic studies, but already at this level you can see this DSS fragmentation function that it follows pretty well. And I don't have here the Hermes and other points, but Boswell will recognize this. One of the curves is from you. So the Hermes points were basically up to here for pi plus pi minus sitting on this curve. So there are no factor 10 differences. Other measurements that are going on, and those are this beam and target single spin asymmetries, which are analog of our PPAN. So it's a big asymmetries coming from many different sources that are not really quantified yet. But some tendency you can notice for these asymmetries that and they are very similar to also the Sivers asymmetry, by the way, has all the same features as this single spin asymmetries for the single target or single beam. You always have very close pi plus pi minus. You always have opposite pi plus pi 0 and opposite pi minus. And normally they are in a very reasonable agreement with high energy measurement. So in this case, class 6 is compared with Hermes measurement. And these are the new measurements. So basically 1% of the data. Those are very easy to measure observables, but not very easy to, as I said, like this PP transverse asymmetry is not easy to interpret. And certainly, I have here just for pi 0, but Rolf was showing for pi plus. And in fact, if you were looking at that picture, you could see that it's actually increasing with q squared, which it's not supposed to do. So it is not a trivial analysis. It requires multidimensional binning. So this analysis of those asymmetries are in progress, but they are huge. They are by significance. They are by far the most significant thing measured in the single spin asymmetry business. And so these are projections for how we can continue from 12 GeV to EIC, which will give us much wider coverage in q squared. So that will be also relevant. If we claim we understand what we are doing, so the q squared dependencies will be critical to measure and make sure that whatever we call higher twist is indeed higher twist. So those are projections for that asymmetries. This is the range that class 12 is currently covering, up to q squared somewhere around 8. Now I want to turn to these medium effects. As I said, the problems that we have with the fixed target experiments, which are with the ammonia targets, so they basically have a lot of nitrogen in the game, and they kind of push us to understand better what is happening with the PDFs in medium. So those are some equations listed here. So it's clear that medium is modifying the orbital structure. So how it is modifying, how should we account for those effects? It is all on experimental. As of today, there is no real any theory contribution, and so experiments have to handle that themselves. Just to give you the flavor, here is what the ammonia targets are. So you basically have NH3. That means 6 times more nitrogen than the polarized hydrogen. So this is what we call dilution is the fraction of the hydrogen in the nitrogen. So basically, we measure most of the events are coming from nuclear modified PDFs, and then we have to sort out, and this dilution factor is a very complicated function of many variables. And to give you impression, here is the 4-dimensional plot for what is called dilution. So this we have to account when we produce polarized target quantities, asymmetries. And you can see that it is a very complicated, so it's xq squared, and here you have z and p. So this is very complicated dependence, and we need a much better understanding of medium modification of these Bartonic distributions. So far, we didn't have any support. Now, the major breakthrough was coming from Shanyan Wang and the collaborators, kind of introducing. So this was basically first quantitative way or introducing the medium modified TMDs that can be used at least to quantify something. So now all our final state interactions, instead of the diquark, will have all the other stuff there. So somehow they accounted all that. In principle, the simple way you can look at these effects is that you just get a little bit wider distributions in the transverse momentum, and those can be visible in many other places. Now, while the target is not a problem for EIC because there is just a proton, but medium modification of TMDs is probably something that should be. This is something that should be in principle in the program, because there is a big nuclear part in EIC, and there is a TMD part in EIC, also GPD part in EIC, but there is no medium modified TMD or GPD part. And to do all this kind of studies in a self-consistent way, definitely will be very helpful, will be very useful for us, and it will be nice to extend this kind of measurement. So what?
Why you are saying that part is not in the...
Do you have medium modified TMDs in the EIC program?
So
do you have or not?
There is definitely medium modification.
Yeah.
Is there?
And there is absolutely in the white paper.
TMD?
Wait, whether the word particular TMD is used, but for sure it is used because we talk about low X, which needs TMDs and gluons, and maybe it's not exactly in the words which you are kind of saying, but absolutely we discuss about medium modifications.
Medium modifications you discuss.
So okay, following what Echo said, that they have a dedicated section in EIC white paper on the medium interaction with the quark or hadron. Hadronization is called. And this calculation, this part of calculation already in the BMPS. If you don't know what BMPS stands for, you have to go there and fix it.
This is the energy loss calculation in the
China had that there.
No.
So PD broadening have been included.
So JLEIC.
Even recently we have shown that you can include this PD broadening into your TMD resummation. So we have some.
Very good. So you can give us predictions for medium modification of TMDs in our X range. I don't want them in the X10 minus 5.
No.
X.1.
No, this doesn't depend on X at all.
Perfect. Fantastic. Fine. Here is the. I just showed that we were getting some kind of prediction for our observables. which is very nice because it was a major breakthrough that we can actually have quantified what is happening with the medium in our case, which is critical. All the cosines obviously are changing. Let's say the sine phi single spin asymmetries are changing. So yes.
Can I make a comment?
Make a comment, please.
So I think the truth is somewhere in the middle. There's been a lot of progress in understanding of what you call medium magnification of TMDs after the white paper, after the AIC white paper. So in the last, I don't know, 5 or 6 years. And in particular, the physics comment I wanted to make, that this model by Xinjiang and company with just Gaussian broadening, this is very, very naive. I mean, it's a good first step, but it's not really true. I mean, what we were fighting with Matt Sivers is that you don't just have a TMD of a nucleus is not proportional. So Sivers function on the nucleus is not just proportional to Sivers function on the nucleon with some transverse momentum broadening. You get mixing. You get mixing. So Sivers function of the nucleus was a Sivers function of the nucleon times some nuclear effects, plus the unpolarized, say, F1 quark distribution of a nucleon with some medium, well, some nuclear effects.
Fantastic.
So it's actually much more
that's exactly what I'm trying to get. So if anything,
that's been around.
Okay, that's actually very good. So what I have here, so we measured, for example, in medium, on proton. There were like some ideas, theories working that in fact the orbital motion is modifying and that is changing something. If you have a theory, it is fantastic, because what we have here was the LOI letter of intent that we submitted in 2014 to study medium modifications of TMDs. And those are all theories that were involved. I was actually happy to see that Zoltang is now kind of a convener, and on slides that JP was showing, there was also medium modification of TMDs there. But our theories all dropped out because they had higher priority things to do. And as a result, all the medium modification business right now in JLEIC it's kind of going as a lower priority business. So any development you have will be great to support this medium business, and will be fantastic. So we are trying to make another wave on pushing through.
So we have, for example, measured medium modification of A sub n over a wide rapidity range from rapidity.
Okay, I know very well your results of A sub n measured there. Let's not discuss that.
No, but they are.
I know all the details of
yeah,
that.
but they are measured even PA polarized. So.
Very good. That is not helping us. Trust me.
That is your opinion.
Okay, it's my opinion.
Sorry,
yeah,
for unsophisticated theorists, why is it not helping?
That is not helping because we first, if you want, we can go into details of that measurement. If you tell me how it is helping me, I will be very happy.
Agree, doesn't help.
Doesn't.
What do you mean? If your goal is to understand how a TMD of a proton is different from a TMD of a nucleus.
This is a story with the
single spin asymmetry.
It's a complicated story.
A sub n in PA, PP is so complicated.
Okay, it's a complicated problem. But
So that doesn't help.
To link,
theory.
we are looking for something that we can quantify, we can use in the measurement, not to say in the analysis. At least to parameterize these effects that I was.
Okay, so the answer to me is you need something more directly coupled to the TMD in question as opposed to the PA. It's a more complicated process, right? That's okay.
Okay. Now the other topic that I'll go very fast through the
2 minutes.
2 minutes.
Well, we live at 5:30.
What is it now?
It's 4:40.
Okay.
Let me
wrap up this. Because I want to come back to this Monte Carlo thing. So I'll go quickly through this. So the other thing is the target fragmentation. So had, I mean, there were predictions, and Sivers effect is to some extent is in fact the correlation between target and current. So, and you expect, and those were predictions that you expect in the opposite, in the target fragmentation region, to show up the leftover pieces and basically some asymmetries, significant asymmetries. This was the prediction. In fact, LK is a co-author of this. That was supposed to make a target fragmentation region relevant for studies, and hopefully that Aram will be back in US to push this target fragmentation business, which is kind of stuck at this point. That the effects of the correlations of target and current fragmentation was there was idea that you can pick up the target, and in that way you can change the current piece. So basically change the weight. If you for example detect lambdas, then you can change what is the fraction of the Kaons coming from S quarks and so on. Those are some distributions. I mean, you go to high PT to pick up something. A target can help. And apart from that, we also measure significant asymmetries when you just correlate a hadron in the current region with the hadron in the target. So those are asymmetries that are significant, and is something that there were also some projections for EIC, but all this stuff is not yet quantified to the level that we would like to bring it to the EIC program as well. This studies of target fragmentation, as the EIC was advertised as a unique place actually that to study the target fragmentation business. This was a theory developed in the meantime for this process involving fracture functions. So more processes, more functions. Obviously, you should not be scared of that. And so this is also something that requires some theory input to bring it to. So basically, results were there, and the suggestion was there to put it in the program, but never converged with that. So because it was not a high priority for the theory community. Now, extraction part, like I have a couple of slides, and maybe I can just move later on to validation procedure. So we have seen this kind of projections plot. So normally we see that these tiny error bars, and every time we have to complain about the error bar showing up here, which doesn't have a bunch of systematics, that sometimes error bars on the complicated observables like transverse or Sivers are smaller than for the unpolarized distributions or polarized or G1. Also, similar pictures here that are not giving you real information whether you can study things like Q-square or PT distributions, and how that will affect on systematics of extraction. So at this point, it's not clear what kind of precision we need. Because we don't really have this procedure that will extract and give us, so for this particular background condition, this kind of contributions, your systematic error on your extraction will be this and this. So obviously, these tiny error bars, they will not survive once you confront it with real measurements with real backgrounds. Okay, this is what our extraction procedure currently looks like. So we ignore everything that is not well understood. But the point was that even if we ignore, we should have some tools to actually account for the stuff that we done. And that all these different contributions, they also contribute through radiative corrections or other effects in the measurement that we are doing. This is I can probably move to the Monte Carlo discussion over. I will merge it with the other slides then. So I'm done with that, right?
Yeah, we thank you now.
Oh, okay, just make me let me make the case that the Monte Carlo is important and how you can use it, and then I'll go to my summary, which let me read it, and then we move to the Monte Carlo discussion. Okay, so different. I mean, we have many communities in EIC, and different communities have also some kind of different focus. And our main focus is the Nucleon structure and understanding of strong interaction, especially when Rick was saying that we will bring the QCD to the level of QED understanding of the proton that can use some applications. Certainly, first thing will be to understand its non-perturbative structure. Now, the points here is that we need really much better framework for measurement and understanding of medium modified TMDs. This was one point. Another thing is that we have to extract our own fragmentation functions. We cannot just rely on some abstract fragmentation functions, extract it somewhere for understanding the systematics. That the fragmentation functions may not be exactly the same. We already had some exchange with the SASO, and so we're willing to add, because huge amount of data will come. Obviously, it will change all kinds of fragmentation functions that were around. Now, the main statement here is that, which I will try to elaborate more in the discussion session, is that we need this extraction procedure that will have estimation of systematics in it. So you can actually account for things that you throw away or you ignore, or things that you account, but there are a bunch of other ways to do that. So the very flexible Monte Carlo, you heard Marco Radici, all his Titanic work they are doing with adding something, subtracting, huge amount of work going into trying to validate what they do and how that is different things, how they change the systematics of extraction of the transversity in this example. So obviously, with EIC, we will have a much better separation. So certain problems that we have at, for JLab12 will be gone. But a lot of other things will stay there. So we'll still have the correlations of the spin, the momentum. We will have, apparently this cosine phi will not disappear anywhere. So far it doesn't look like it's disappearing. So which means that this Quark-gluon correlations will be also there. So it will be important to understand. And so the statement here, I think it is very important that whatever version of the EIC we will run, it should overlap in kinematics with the JLab12 to help us understand what exactly we were doing at JLab12. So this will be important. Okay, thank you.
Before there's a discussion for this?
Well, I actually wanted to put it to a vote because we kind of ran late, and one option would be to postpone the discussions tomorrow.
Okay.
But
then we can
could you finish your
open for
sentence?
questions.
Yes, we could probably.
Okay.
I just make comment when you share this solid predictions, there are top-class systematics. There are the experimental systematic we already considered. They are
Which experimental systematics?
You can look at, we have a list of experimental systematic errors, and we all considered. The beauty with
Like target fragmentation contributions?
no. I'm talking about first experimental observers.
I'm not saying that nothing is considered there. I'm saying there are a bunch of things that are not considered.
Look, if you go back to your slides, the experimental observers, that's where you have the asymmetries, current asymmetry. These experimental observers, these we consider both systematic and experimental. To go from there on, that's a different story. And
No. It is also sitting there. It is also sitting there. For example, we were discussing very simple things, right? So when you do your simulation, you have just your Collins and Sivers, right?
No, we do
So, for example,
the
systematics.
5-term extraction.
Systematics coming for this measurement, particular Collins measurement,
Yes.
coming from the radiative correction through sine phi s azimuthal moment is not considered. That cannot be considered because we don't have it.
We did some estimations, not fully considered for you.
JP, this was not to offend you. This is just to make a statement that things are complicated and we need the procedure to control things. That's very, very simple, simple statement. You were doing things at state of the art. No complaints to what you do. The same thing is our EIC projections. They were all correct and done properly in the way they were done. But we learn things. We learn things that are certain things. People are improving the systematics, going through this procedure of running and rerunning of things that increases our experience in the things that we have to account, how we should handle that.
But I want to make comment that there are part of this a little bit under control. Then the other part to go from your measurement. In measurement, it's true that the radiative correction is always the issue with coupled with your model and all that. But go from there to extract your final distribution. That's different story. You have a lot more uncertainties, systematics. So I just you just dismiss this error is not. We did consider all the systematic certain level.
I'm sure you did. I'm sure you did. That is not the point. So there are certain things in the systematics that you need theory. So simple things like your acceptances, efficiencies, and that kind of stuff. Obviously, you will take into account. But then you have, if you have an H3 target, then you have uncertainties coming from the handling of the medium modified distribution. So you will not have just your hydrogen there, for example, right? In helium, it's a simpler case, it's cleaner, but you still have in helium also something is modified.
This, yeah, so this is our dominant error is from the helium, which we work with theorists, and that is estimate. Is our dominant systematic errors. It's in there also.
So you have medium modified helium TMDs?
Yes.
Really?
Yeah, the Roman group gave us their estimations. What uncertainties, not
as a function of PT and everything, and you have that.
Yeah, they did this estimation. Turned out in the asymmetry, it has a large cancellations. The effect is not as big as in this TMD itself. But if you do just the stretch function itself, the uncertainty is at the level of 10–20%. In the asymmetry, it's only at the level of 5%. I can show you the
plate-based close approximation.
it's a relativistic, yeah.
But they have it. Because it's a free body system, they can do it.
Yeah,
Only
they
at some level.
did this. I can show you the paper published last
Maybe I
year.
missed it. I hope like in X you have something, but you have also.
There's still
We
a
had,
certain-
they also come to this INT workshop. We discussed that.
Very good.
So to be fair enough, I think last week we had a lot of discussion on systematics, what origination, in particular high Q score. And JLEIC definitely limited by Q score for SIDIS.
Yeah,
so
that
we do need a high Q score to make sure that we have TMD calculation work, which is solid. And I think the EIC definitely would provide that kind of important information to cross-check.
Yeah, that's a
Let-
different issue.
let-
That's
I
not the
agree with-
meaning dependence. That's true. Every
No, even more than that.
Oh, I agree. Yeah,
Depends,
but-
for example, how you get rid, how you kind of eliminate high-trace contribution,
Everybody
target
knows that.
fragmentation contribution. So
Absolutely.
only way you can do that is go to high Q score.
No, exactly.
Yeah, that.
So
Yeah,
that's
I'm just trying to make it.
That
yeah,
is
that was
that is absolutely true. That higher you go, less are those. But
Yes.
this low Q square is the place where you can try to quantify them in some way, right? Then you have to check whether like Q square 10 is good enough or not. Right?
I have a whole talk on those.
There are
talk I can give.
First, you identify the complication and you try to find
certain part we cannot do. We did the part we can. The other part we do need a theory help, need high Q square help. That's absolutely true,
Yes.
right? Not try to dismiss that part.
Yeah, but again, until you will not measure the Q square dependence of something, you will not understand what is a high Q square.
Any other question, comments?
See, there's all kinds. Yeah,
That's true. I only have one comment that you show Q square dependent on symmetry. You still use Alex's older prediction, which was wrong, right?
Oh, I thought he corrected it in some way because it is like now different than it was before. But if you have a better version of that, I mean, it is for sure it is a very important thing to understand how this thing is changing. So this error bar is good or is not good. It depends how much what is the effect, right? So that was one of the things to quantify the Q square dependencies to make sure that the statistics we have is enough for that, or we
I'm just saying that.
You send me. You say if you have a better.
No, I definitely have, but what I'm saying that what the curve you use is totally wrong. That's what I'm saying.
Very good. Send me the right one.
I told you many times. Anyway,
Okay.
any other
Very
comments?
good.
Okay, and thank you, and
Okay, so the plan was to have a discussion now, but we're kind of running too close to leaving for dinner. So what's the feel in the room? Do we want to have a brief discussion of Monte Carlos for 3D extraction, or should we just punt until tomorrow?
It'll be very short. I actually have only very few slides. I make the point, and then we can.
We were aiming at finishing the discussion by 5 o'clock. Correct. That was our original plan. Yeah, so what? Any feelings in the room?
We'll do it tomorrow.
Okay. Anyone feels otherwise? Anyone wants to have a discussion now?